Hello and welcome to what is essentially supposed to be a review of exponent rules, although depending on what you did for pre-algebra, some of these may seem pretty new to you. So hopefully either way you're able to get something out of this, and we're just going to kind of go through and talk about what do we do with basically like x squareds, x cubes, things like that whenever they're, around each other interacting. So let's check it out. First off, actually, let's just talk about exponents in general. So here at the top, I've got some bubble letters here that look fancy. Whenever we have something like 2 to the 4th power or x to the 2nd power, the bottom number that is usually in like a normal size font, which in this case would be b, that is called the base of our exponential expression. Before now, you probably have heard of the word exponent because we typically see that actually pretty early on, like somewhere around the time we introduce decimals is when we usually start talking about exponents. So what that means is that I think the word exponent should be familiar to you. There's another word we use for it in math, which is power. But whatever word you want to use, that's what it's usually a smaller font. It's up and to the right. We call it a superscript. In, I don't know, it's probably not specific to computers because probably you would use the same word for like whenever there were typewriters, not computers. I don't know, but exponent or power would be a word up here that we could use. And what this means when we have something like b to the n is they're telling us that we have repeated multiplication. Now, n is not actually a number, it's a letter that's supposed to say, hey, this could be any number. So that's what this ... here is for, is to say like b to the n is b multiplied together n times. So actually maybe that's what was supposed to go in that blank. I'd forgotten what was supposed to go in that blank, even though I made this myself, so maybe that's what was supposed to go there. The way we read exponential expressions most often is we just say, like in this case, b to the n. And there are a couple specific words, right? We have for powers like squared for the 2nd power and cubed for the 3rd power. And that's partially just because those are the ones we use so much. And both of those words have to do with the idea of geometrically, like if you have a square, you have a side times a side, which is the same as having something squared. If you have a cube, and you're talking about like volume, you would do side times side times side, which is cubed, or to the 3rd power. So there's a reason why it is the way it is, but just those are the only two that we have special names for. So that's the idea of exponents and exponential expressions. Now, the other thing we need to make sure we understand is how exponents actually work. So I'm going to start here kind of on the right side of this chart I've got. We're using 10, so this should be relatively easy, at least once we remember how this works. So I'm going to start with 10 squared, which might seem like a random place to start, but that's where I want to start. What is 10 squared? Well, squaring means to do 10 times 10. 10 times 10 is 100. And I started there to kind of remind you, there's this trick with tens and exponents where whatever the exponent is, that's how many zeros we should have. So when we do 10 cubed, which is 10 times 10 times 10, we should end up with 1,000, which happens to have 3 zeros. Now, 10 to the 1st, so my hope is that you remember how the 1st power works, but if not, here's kind of the explanation. When we have 10 to the 1st, we're being asked to multiply 10 together one time, which means we don't need to multiply, we just have a 10 itself. Like 10 squared means 10 times 10, 10 cubed means 10 times 10 times 10. So 10 to the 1st means 10, and that's it. So 10 to the 1st is 10. So we need to be able to figure out and have something make sense for having a zero exponent or negative exponents. And so I think it's fascinating, personally, the way this works. You don't have to think it's fascinating. But the way to kind of come up with it and prove it to you, what it is that we're just going to work backwards and look for a pattern, because math is all about patterns. So I'm going to start from the right side of the chart. We already know these three answers. We're going to say, how can we get those answers without paying attention to the exponents? So how do I go from 1,000 to 100? And how do I go from 100 to 10? And that should be the same answer. Like, what's the pattern here? What am I doing if I try to go backwards? If I'm going forwards, if I go from 10 to 100, I'm multiplying by 10, right? 100 to 1,000, I'm multiplying by 10. But if I want to go backwards, 1,000 to 100, I'm dividing by 10. And the same thing is true. 100 divided by 10 is what gives me 10. And this is going to help us because now we can say, well, whatever 10 to the 0 power is, it should be what I get when I do 10 divided by 10. What do we get when we divide 10 by 10? We get 1. And it actually turns out that no matter what I had put in this chart, the same sort of thing would have happened. That whatever number our base was is what we would be multiplying or divide by to move back and forth. And so whatever to the first power, we'd have to divide by the base, and we'd end up with 1. So what that means is that anything to the 0 power is 1. Any number, any letter. Now, there's actually a small caveat here that 0 to the 0 power, we don't really do that because there's just it doesn't come up like the other ones do. I don't know how else to explain it. It's kind of like how we have that over 0 situation is undefined. That's what it's closest to. You should not be encountering 0 to the 0 power, so it shouldn't really matter to you if that's 1 or 0 or undefined or whatever. It shouldn't happen to you until calculus, and then you learn how to deal with it, so it's fine. Now let's keep going. If 10 to the 0 is 1, how do we get an answer for 10 to the negative 1, and what would that answer be? Well, let's keep doing our pattern, right? We want to take 1 and we want to divide that by 10. And there's two ways we can write that answer, because when I do 1 divided by 10, I get 1/10, which is either a decimal or a fraction. And if you say 1/10, you actually could be talking about either one. So 0.1 or 1/10. If we divide by 10 again, now it might start being tricky unless you remember kind of the trick with dividing by 10 that moves the decimal over each time, one more to the left. So like 0.1 divided by 10 is 0.01, which is the same as 1 over 100. When I divide something that's already a fraction, it actually affects the denominator. So 1/10 divided by 10 actually multiplies the denominator by 10. So that's how that's happening. And then 10 to the negative 3 is 0.001 or 1 over 1,000. Now let's actually notice something. 10 to the positive third, I wonder if I could actually point strategically here. 10 to the positive third and 10 to the negative third have a similarity thing happening here. 10 to the positive third is 1,000. 10 to the negative third is 1 over 1,000. And then look in one step, right? So 10 squared is 100. 10 to the negative 2 is 1 over 100. Interesting. Look in one more. 10 to the first and 10 to the negative first. They're the same. It's just that the negative exponent is putting the 10 on the bottom instead of on the top. So we actually have this whole thing now then that we can do that revolves around positive and negative exponents, where we can say, if I have a negative exponent, I can make it positive by moving it down to the bottom. I didn't necessarily mean to put the equal sign right there. I move it down to the bottom, and then I can think of it as a positive exponent and say, okay, what is 2 cubed? 2 times 2 times 2, which is 8. So that would be 1 over 8. I think one of the reasons that we kind of struggle with this is that we already kind of struggle with exponents. If you've ever been asked, like, what is 2 cubed, and you've answered 6, like, you get it, right? You have to, like, purposefully remember, okay, it's not 6. It's not 2 times 3. It's saying 2 times 2 times 2. And you actually have to sit there and, like, figure out what is 2 times 2 times 2. So it's got that against it. And then we throw in negatives, which we already don't really like negatives as much because it made everything more complicated. And then you're saying that negative exponents don't actually make anything negative. They just make it a fraction instead, which of the things to turn something into, fractions would probably be the last thing we'd want to turn things into. So I get that it's frustrating, but it's so cool in the broad scheme of math that this is how it works, that we can notate it this way and that it makes sense for algebra and for calculus and for everything. Sorry, I have an appreciation for this and I don't know why, but it's really awesome. So what we're going to do in this exponent review that we've got is we're basically going to talk about simplifying exponential expressions. And there are some rules that we can use to help us do that more quickly. So I'm going to show you here's the long way to do it and why it works the way it does. And then I'm going to say, well, this is the shortcut. That if you can remember the shortcut, it's faster. And the shortcuts aren't unreasonable to remember, I don't think. So we're going to give it a shot here. This chart has all of kind of the rules for exponents. And so we're going to go ahead and start with the first three. And then we'll look at the rest, I think, in a separate video. So that if you want, you can take a break between and not feel bad about pausing a video to take a break, that you can actually have a break between them. So when we have something like x squared times x to the fourth, here's what that means. It means we have x squared, which is x times x. And then we have x to the fourth, which is x times x times x. Now, an exponent is just an attempt to show us how many times we're multiplying together the same thing. So if I have x squared and x to the fourth, I have 2 x's and then 4 x's. And so together, we're really multiplying together how many x's? The answer to that is 6. So that's kind of the long way to take something like x squared and times x to the fourth and say, oh, that simplifies into x to the 6. And by simplify, we mean we can write it with fewer strokes of our pen or pencil. I mean, just pencil. We can write it in a shorter way, right? By making it x to the 6 instead of it being x squared times x to the fourth. But let's think about how we can maybe make a rule and a shortcut for this so we don't have to write this all out. And you may have been thinking of it as you wrote it down or as I wrote it down, because if we have 2 x's and now we have 4 x's, together we have 6 x's. What have we just done? We've just added our exponents together. 2 plus 4 gives us 6. So if we have two things that are the same base, so it doesn't work if you have 2 cubed and 3 cubed. You can't do this trick with that. But if we have the same base, we can combine it into one single expression if we add the exponents together. Okay. That's the first rule. Second rule has to do with having a power that is then raised to another power. So what if I want to do x squared to the fourth power? What does that mean? So I'm going to try really hard to make this clear because there's a place here where I can lose some people. So I'm going to see what I can do. So x squared to the fourth power is telling us to do x squared 4 times. But if I write it this way, as x squared 4 times, I no longer have it raised to the fourth power. Now I can think of it as, well, how many x's do I have? Okay, I have 2 x's, and then 2 more x's, and then 2 more x's, and then 2 more x's. How many x's do I have? I have 8. Now I could have gone a step further and written each of these x squareds out as x times x, right? So what's happening here is this is really x to the 8th. So if you start off here and notice, okay, I have a power to a power, what that actually ends up doing with our exponents is it makes them you end up multiplying them together, and that's what gives you your new exponent. So it's basically saying I have x squared, but I have it 4 times. So how many x's is that really? 2 times 4, which is 8. So here I'm going to put x and then a times b. So there's kind of 2 approaches, these problems in general, there are multiple approaches too, in a way that we maybe haven't seen much before or see soon after this. Literally, in these problems, if you get the right answer, you probably did it a way that is correct, unless you're just making stuff up and just happen to guess right. Whereas normally there's a thing that I can be this is how you do it, right? But that's not necessarily the case on these. So we can say I have x squared 4 times. that means I need to do 2 times 4 and get 8. Or we can write it out and say, okay, x squared, x squared, x squared, x squared, and add the 2's together, and we still get 8. Those are 2 different kind of ways of approaching this that use both the first and the second rule. Like one of them uses the first rule where we add the exponents, but that's because we expanded it. We wrote it out so it was no longer x squared to a power. It was now just x squared, x squared, x squared, x squared. Or you can just leave it as a power and say, okay, I'm going to multiply those together. Our third rule that has to do with multiplication here is if I have something like x times y and it's to the third power, what does that mean? Is there a shortcut to that? Because the long way to figure it out is to say, okay, I have x times y, and then I have x times y, and then I have x times y. And so what does that end up being? Now you can't combine x's and y's, right? So we'd say, well, I have x, x, and x, and then I have y, y, and y. Because it's all multiplication, we can like rearrange it so that we can group them by x's and by y's. And that lets us write this as x cubed, y cubed. This may be where we could argue about whether this is simpler than this in some ways. It ends up being more that like when we have parentheses versus when we don't have parentheses, there usually are more things that we're able to do whenever we've gotten rid of the parentheses. So that's kind of why we do it. So what's happening here is you can kind of think of it like a distributive property, sort of, that everything inside of our parentheses, because our parentheses has this multiplication happening, has to get that exponent. It actually works completely different if it's a plus sign in between. So please notice that nowhere in this are we adding or subtracting our actual like exponential expressions. Yes, we're adding our exponents together, but that's not the same thing. If it was x plus y to the a, this would be way different. But since it's x times y to the a, what we're saying is that we can write that as x to the a, y to the a. Now we're going to go and look at some examples. I've got lots of examples. You may not need all of these examples, that's fine. But I want to make sure we got some examples here. Okay? Usually instructions in this sort of section say simplify. Your answer should contain only positive exponents. And so we did talk about negative exponents earlier. So this is just a way for us to basically come up with the same answer without introducing the idea that, well, you could have an answer that has negative exponents and mine might not, and they could be the same thing, but they look different, that kind of thing. So let's see. A says simplify. Based on the rules we have, there's more than one way to do this. But essentially, it's saying we've got 4 x's, and then we've got 0 x's, and then we've got 3 x's. So how many total x's do we have? So if I do 4 plus 0 plus 3, I get 7. So this simplifies to be x to the 7th. You also could, anytime you see to the 0 power, you can take that and mark it out and put a 1 where it is. And then that might make things easier. So anytime that creeps up, something to the 0 power is 1. So you can like basically make it not even be a thing anymore. How about B? Y cubed to the 4th power. So this isn't saying y cubed and y to the 4th. This is saying we have y cubed, but we have it 4 times. So how many y's do we have? If we have y cubed, we have it 4 different times. We actually have 12 of them. So this is y to the 12th. If you are struggling with this, my best suggestion to you is to sit here and write it out. If you're not understanding how I got x to the 7th, you should write this out as x times x times x times x. That's x to the 4th. X to the 0 means I have no x's, so we wouldn't write anything for x to the 0. X to the 3rd would be x times x times x. And then we look at this and say, okay, how many x's do I have? I have 7, so I write x to the 7th. In a similar way with y cubed, we could say, okay, well, this is y cubed. I mean, it's not fun to rewrite it a whole bunch. That's why we have the shortcuts. But y cubed 4 times. Okay, can you figure out why it's 12 now? If not, keep going. And I don't want to do this. And make it y, 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 and y, y, y. And then we have 12 y's, right? So that's why it's y. That's why it's y to the 12th. Okay, let's try C. So we are going to square everything inside of our parentheses. Now, what's inside of the parentheses here, each of these things, we've got 2, we've got X, we've got Y, we've got Z. All of those are being multiplied together. So that's why we're allowed to basically drop our parentheses and say this is 2 squared X squared Y squared Z squared. And because we know what 2 squared is, if we think about it, we usually go ahead and make that change. This is 4x squared, y squared, z squared. And the reason everything gets that squared is because all of it's in parentheses. If I had anything outside of my parentheses, it wouldn't be affected by the squared. Exponents only affect the thing right next to them. So for instance, the x to the third on the first one of these, that third power doesn't affect the x to the 0. It's not just because I put a dot there. I could have left the dot out and it still would have mattered. Like, what I'm thinking of, I guess, is if you have 2x cubed like this, the cubed is only affecting the x. If we wanted to say 2x cubed where the 2 needs to be cubed as well, we have to put parentheses around it. Okay, that's an important sort of distinction that we've got going on. This is the gist. Okay, we can make this more complicated or just do more problems like this, but I'll tell you, this is the gist. I am gonna go through and do more problems with you. But this is the point where you might try to see if you've got the hang of it, or just keep listening, whichever one makes more sense for you. All right, so we've got things that are a little bit more complicated here maybe. So we're gonna start with this first one, and what's important to remember here is that all of this is multiplication. So when I do 2x cubed, this is actually why I brought this up on the last slide. When I have 2x cubed, I'm saying 2 times x cubed. And we're saying times 5 times x squared times x. I want to point out, we could put dots between every single one of these things, or we actually don't have to put dots between any of them. Now, putting x cubed and 5 right next to each other is not something we normally do. But my point is that it's all multiplication. So we can rearrange it if we want to, because multiplication can be done in any order. 2 times 3 is the same as 3 times 2. You know, you can switch it around, you can move them, and it's fine. That's called the commutative property of multiplication, maybe. So what we can do is we can say, I'm going to take the 2 and the 5 and multiply them together because they're both normal numbers. And then I'm going to take the x cubed and the x squared and the x and put them together. Remember that if we just have a regular x, it does have an exponent that we don't write. It's to the first power. So 2 times 5 is 10, and x cubed, x squared, and x, we add those exponents together, or we write it out and count them. We get 3 plus 2 plus 1, which is 6. So this is 10x to the 6th for this one. Okay? So we are going to cube both of the things in here. So cube this one and cube this one. So 2 doesn't have an exponent, which means it gets cubed. But y to the 5th has an exponent, and it needs to be cubed. So we're going to have to do 5 times 3. We have y to the 5th, but it's saying we have that 3 times. So that's going to be y to the 15th. So 2 cubed is 8, and then y to the 15 is going to go next to that. So here's our answer, 8y to the 15th. This one, same kind of deal. And so this one I don't feel like has anything extra to it. We're going to cube everything inside of our parentheses. So let's see. I'm going to cube the 5. That's 5 times 5 times 5, which is 25 times 5, which is 125. And then x also needs to be cubed. So that's x cubed. And then y squared needs to be cubed. So if you cube y squared, you have y squared 3 times, so that's y to the 6th. If I do that with z cubed, having z cubed 3 times means I have z to the 9th. So this is my answer. Okay, so this will be our last 3 for like multiplication, and I'm going to end the video. You take a break, and then come back, and hopefully sometime soon after I upload this video, the other video will be ready, and I'll upload it as well. Okay. So this is starting to look complicated. I mean, actually, like, just G, I think, looks more complicated. The other two look really similar to what we did on the last slide. So we've got regular numbers, 2, 8, and 3. We've got m's, and then we've got n's. So we treat those basically as 3 separate questions almost. We can do 2 times 8 times 3 and figure out what that is. And then we can figure out, well, what's m to the 4th, m, and m. And then we can do n to the 9th, and n. And then we can figure out, okay, what is this actually simplified to be? 2 times 8 times 3 would be like 6 times 8, so that's 48. M to the 4th, m and m, which both of those would be to the first power. That means we have 6 of them, so m to the 6th. Then we've got m to the 1st, n to the 9th, and n to the 1st. That would give us n to the 11th. Okay? Now, like I said, these other two aren't really necessarily that much different from what we already did. So k squared to the 5th power, well, we've got k squared 5 times, so that makes k to the 10th. Let's see, 3 to the, we're going to do the 4th power on all of these. 3 to the 4th power is 3 times 3 times 3 times 3. So we could say that's 9 times 9, which is 81. Y to the 6th to the 4th power would be y to the 24th. Z squared to the 4th power would be z to the 8th. So that's our answer there. So, gonna stop the video here. Thanks so much for watching. As always, please subscribe, like the video, and be sure to stay tuned for the next video, which we'll talk about whenever we have division or when we have negative exponents, and it's gonna be a great time. Thanks.